Hello, students. Let me start with a curious thought. Have you ever wondered why the ruby in your mother's jewelry has such a deep red color? Or why some crystals of sodium chloride glow yellow when heated? These fascinating behaviors are not random. They arise due to tiny irregularities inside the crystal lattice, which chemists call imperfections. A perfect crystal would have every atom or ion neatly arranged in its ideal position. But in reality, nature always leaves its signature of irregularity. These irregularities, or defects, can dramatically change a solid's electrical, optical, and magnetic properties. In today's session, we will explore these imperfections and see how they are classified into electronic defects and atomic defects.
At absolute zero, a crystal behaves like a flawless insulator. But as temperature rises, electrons gain energy and defects appear. Sometimes, an electron is knocked out of its position, leaving behind what we call a positive hole. In other cases, extra electrons may slip into interstitial spaces, creating special sites known as F-centers. Let's take the example of sodium chloride. When it is heated in the presence of sodium vapor, electrons get trapped in chloride vacancies. These F-centers absorb visible light, making the crystal appear yellow. Isn't it amazing? A simple electronic defect can completely change how a crystal looks and conducts electricity. Now, let's move to atomic imperfections, also known as point defects. These occur when atoms or ions are misplaced around a lattice point. There are three common types. First, the vacancy defect, where a particle is missing from its normal site, leading to a decrease in the solid's density. Second, the interstitial defect, where an extra particle squeezes into an interstitial site, increasing density. And third, the impurity defect, which occurs when foreign atoms or ions enter the lattice, either replacing or occupying interstitial positions. For example, doping sodium chloride with strontium chloride introduces strontium ions that create cation vacancies. These point defects are key to tailoring the physical properties of solids. In ionic solids, sometimes defects appear without disturbing the ideal cation to anion ratio. These are called stoichiometric defects. The first is the Schottky defect, where equal numbers of cations and anions are missing. This reduces density. It is observed in ionic compounds like sodium chloride, potassium chloride, and cesium chloride, which have high coordination numbers. The second is the Frenkel defect. Here, a smaller cation slips into an interstitial site, leaving behind a vacancy but keeping density nearly unchanged. Compounds like silver chloride, silver bromide, and zinc sulfide often show this. So, Schottky reduces density, Frenkel does not, a small difference with big consequences in conductivity. Not all solids obey perfect stoichiometry. Some show non-stoichiometric defects, where the ratio of cations to anions gets altered. One type is the metal excess defect, which arises when there are extra electrons in the lattice. For example, zinc oxide turns yellow on heating because oxygen escapes, leaving behind electrons that give color and conductivity. Another is the metal deficiency defect, where cations are missing, but neighboring cations balance this by changing their oxidation state. These defects explain why certain compounds exhibit unexpected colors, magnetic properties, or semiconductivity. It's like the solid develops its own personality by bending the rules of chemistry. Another fascinating class is impurity defects. When foreign atoms are deliberately or accidentally introduced into a lattice, they replace the host ions or occupy interstitial positions. For instance, when sodium chloride is doped with strontium chloride, strontium ions replace sodium ions and create cation vacancies. In fact, doping is the principle behind modern semiconductor technology. If we add trivalent boron into silicon, we create p-type semiconductors with holes as charge carriers. On the other hand, doping with pentavalent phosphorus introduces extra electrons, forming n-type semiconductors. These small tweaks are the backbone of electronic devices, from your smartphone chips to solar panels. So, let's quickly revise. Imperfections in solids are irregularities in their crystal arrangement. They are classified as electronic, atomic, stoichiometric, non-stoichiometric, and impurity defects. Each type has a unique influence, from changing color and density to controlling conductivity and magnetism. Real-life examples abound. The yellow hue of heated zinc oxide, the sparkle of colored gems, and the working of modern semiconductors are all rooted in solid-state defects. I hope today's session helped you see that what seems like an imperfection is, in fact, nature's way of engineering extraordinary properties. Until next time, remember, chemistry is not just about equations, it's about the hidden order and disorder that shape the materials around us. See you in the next class with more fascinating insights into the solid state.